Okay, good morning everyone. Welcome back today. Thank you very much for yesterday. And we a little bit shorter day than planned today, sorry for that, but we'll be effective today and try to capture as much as possible. So I just get started right away, and we continue where we left off yesterday. We're going to talk about start with talking about cost-effective decision support for different alternatives, which is really one of the basic questions that we have when working with OPUS Suite, right? We have different alternatives and we need some decision support. So here the question is, we have two different options for this helicopter engine that we were looking at yesterday. So let's say that we're about to acquire a new engine for this helicopter or evaluate two different designs or so. And we want to know which one is the most cost-effective option from a life cycle perspective. Okay, so is that possible? Well, yeah, with the data from the manufacturers, we can perform comparative analysis. We can compare the alternatives, and that will make us able to support the decision in the end. Okay, so we have two different alternatives here. We simplify, we call them X and Y, and they have different characteristics in terms of mean time between failures, time between PM, different price of the components, spare part prices, lead times, the repair costs, also turnaround times and resource investments. All these things vary between those two alternatives. And I just leave it with that and we'll move to OPUS Suite and I'll show you how we can compare these alternatives. So I've been thinking all night about this setup with a microphone and how to sit and see everything. So I hope this works out well today. So anyway, prepared those two files. We have one for the Exalt. So these are the, as you recall from yesterday, the input files for OPUS 10 here. We start there. And we see that we have two different files for the two different alternatives. And I can open up both of them at the same time here, as you saw. And now it's, as you know, the model consists of many different tables and inputs, and it can be hard to understand what the actual difference between those two files, what those differences are. So one of my favorite functionalities in the tools, very basic functionality, but I think it's really helpful, is something that we call compare files. So what I can do here is I click the data command. There is this compare functionality here. Since I have two files open already, I'll just show you here, go to the end of that one. You see that this is the engine Y alternative. And that file is going to be compared with the engine X alternative. I hope you can read. I know it's kind of small, but so anyway, those were the two files that I had open now. So they were selected directly, but I can of course move in here and select any of the input files that I want to compare. And then I want to match the keys, so the identifiers, from all the identifier columns, I want to match them. So even though they are on different separate rows, I can still match them. And that's all I need to do, and just click OK here. And then I get a list down here in this beautiful log window at the bottom, where we yesterday were looking at some warnings and errors and stuff like that. But here you see there is different tabs. So here we're looking at the compare tab, where we end up, and we get a list of all the differences between those two files, sorted per table. So here you see the first table where it differs is the PM interval table. I didn't show you how to input PM yesterday, but let's look at it. So I just double click that one, and I'm going to switch to the table view rather than the model view because my screen is a little bit small here. So we can do that here. Toggle the model view is this button here. So they're going to only do the same thing for the other files. So now I'm only showing the table itself, the data in the table. Okay, and you see here, as it says, the column P and int, the value is differing, and that's the time between the preventive maintenance scheduled tasks. So it's 1,000 for the Y alternative, and it's only 800 hours for the X alternative. And then it continues like this, so I'm not going to show it to you all, but for example, the failure rate values differ, so I double-click that one, and I can see the differences here. And this functionality it can be used in many cases. For example, if you've done some changes and you want to see what that was, and I mean, it's not only when you're comparing to alternatives like today, but it can be in many situations where this is valuable, I think. So, and here, if you remember, when we have items that we cannot repair, but we have to buy a new one, it's associated with the lead time. So you see here, it differs. It's 730 hours for one and 900 for the other. Also, the setup cost for that ordering is different between files. So, I'm not gonna, as I said, we don't have to go through all that, but here's the list of differences anyway. So what I can do now is to, here, I go to the tools, and there's something called calculate all. So if I work with multiple files at the same time, that's a command for running the calculation on many files at the same time. To do that, you see, we get two curves right away, and maximize the window. And we see our two alternatives, engine X and engine Y. Here from this view, it's kind of obvious that one of the alternatives is more cost effective than the other, right? So if we have, let's say we have some requirement of 95% availability for this helicopter engine, I select the first point, about 95% here, and you see that if I add the difference between the points. Here it is, to show the delta. You can see that there is a difference on around 200,000 euros in this scenario, and for the same availability. So engine X is cheaper or less expensive than the other one. So in that terms, we can reach the same availability for a lower cost. Okay. And then you wonder, of course, but what costs differs, and what's the difference between those two actually? Then we can go to the cost analysis part. So I'll just open up those same two files. I can link the data here. I think I showed you that yesterday. So I have two files that are linked to the results from the optimization, and so I can select the points directly. But here I just again run both of them at the same time. And we get the results. So here is the lifecycle cost, just changing to that same the LCC value. So, and you see those two figures should correspond to what we had in the graph in OPUS 10 as well. So you see again, the engine X is that alternative is cheaper on a total from a total perspective, and then of course we can again drill down here to see what costs that. How the cost spread looks like. So by opening up here, you can see that the yearly recurring costs for the engine X is actually higher. It's 1.7 million, while it's only 1.6 for the engine Y. However, the investment cost for the Y engine is higher. It's 1.26 million, while it's only 900,000 for the X alternative. So it seems as if we need less spare parts for the X alternative, but we do more maintenance. So we can go in and take next level here as well. Look at the recurring cost, for example, which are the costs that comes every year. We see that for the X alternative, the corrective maintenance costs. See, I pointed here. I don't know if you can read it, but it says corrective maintenance costs. So it's 1.2 million, which is more than 1.1 here. So that's the main difference here between the two alternatives. And then of course we can continue there and look at, I go down one level, and if I select only the C and C here for corrective maintenance costs, I'll see the two sub costs of that one. You remember that we can break down this cost breakdown structure according to how we build it up. And this cost model is the one that is available directly in OPUS Suite. So it's the OPUS Suite cost model. But of course, you can do any adjustments or corrections or additions to these cost models as you like. They are fully user-defined. This is more like a support or for getting started and using a direct functionality. Okay, anyway, looking at that, we see that it seems to be the corrective maintenance cost for items that differs. As you see, there is the main part of the difference between those two. And this way you can continue down and look at that. Next level, so this just to show you how to drill down. And it seems to be for the repairable items again. So you see different, like this one a little bit easier to read. So it's a lighter blue one here, which is item corrective maintenance costs for resources as well. So yeah, corrective maintenance cost and with resources associated. So it seems to be expensive. And this is because, if you remember from yesterday, we connected the maintenance tasks with the maintenance resources. So that seems to drive the cost. And we can use the buttons at the bottom here to sort of dig down to find the cost driving spare parts or cost driving items. So if I move the material button to the x-axis here, that's kind of small, but we see that for both alternatives, it seems to be the afterburner module that is quite expensive because we need expensive resources when we repair this one. So that's why they are sort of driving the costs. Again, this is a really small example with just 8 items, but in a real world case where you have hundreds of items, it's nice to be able to filter out the problematic items and maybe try to do something more about them. Okay, so that was the cost analysis part of this. Any questions? All right, then we can continue. Go back to the all right, so we continue with the next thing to introduce. It's kind of, as I said, high-speed tempo today to cover the topics that I really want to, that you can bring home. So next question is about if we need to re-evaluate the maintenance strategy for the helicopter engine. So what options do we have and which of those options is best? Well, that is kind of, it sounds like a LoRa evaluation that needs to be done. So a LoRa is, that's a kind of a standard concept, which stands for level or location, depending on who you ask, but level of repair analysis, as it says down here. So it's about understanding where to perform which maintenance, okay? And if we so take a closer look at this, when we have an organization like this, we do need to perform different maintenance tasks, as you know, but it becomes many different alternatives here. So for example, looking at how can we replace stuff or repair items and also replace them. You remember we have replacement tasks and rectify tasks. So one is when we take it out from the system or from the parent component. The other one is when we actually fix it. So those tasks needs to be defined where they are performed, and we might have different alternatives. Same thing if we have to reorder items that are non-repairable. We also need to understand on what level is it most cost efficient to perform these actions. So that's sort of the classic LoRa, to decide where to do which type of maintenance. But we are not only interested in that, we are interested in spares optimization as well. We want to know where to store the spare parts, how many of each, and at what location. So that's the spares optimization or allocation. And then third, we also have the resources, because resources are often needed to be able to perform the maintenance, and those can also be allocated with a number and at different locations. Okay, but the thing is that those are 3 different tasks. So deciding where to perform the maintenance, where to store the spare parts, and where to allocate the resources. But the thing is, which is very important, that those 3 will affect each other. So the number of spare parts will affect where we perform the maintenance will affect how we should store the spare parts in the best way. And also, of course, there's no reason to have a lot of resources at the workshop or at the sites if we're not performing any maintenance there. So it all really, it's joint decisions. They are all connected to each other. They all play a role together. So that means we need to understand this at the same time. We need to draw the full picture, understanding where to perform the maintenance, where to store the spare parts, and where to allocate the resources. So it's a strongly connected decision. And again, of course, we want to measure this according to the cost and the effectiveness. So finding cost-effective solutions, how this all plays together. Okay, and so if we look at those three tasks that we want, as analysts, wants to perform, the spares allocation is typically classic OPUS 10. That's what we have seen now yesterday as well, that we can understand where to store the spare parts. And performing a maintenance concept optimization is a classic LoRa task to just look at where do we perform the maintenance. And understanding where to store the resources, or allocate the resources, that's what we can do with OPUS 10 and Simulux as well. But the important part here is to do all these three at the same time. Is something that we can do with it's a built-in functionality of OPUS 10 called LoRa XT. So it's not just a LoRa in the classic concept, so that's why we call it XT for extended. So it's an extended LoRa analysis where we can do all those three things at the same time. It's a combination of tasks, and this is something that actually makes OPUS 10 unique. I'm not aware of any other tool that can do all those three things at the same time. So as you hear, that's something that we are proud of. Anyway, if we take an example on how this can work, we look at the engine system that we're looking at here with a set of items, and then here is another little bit more evaluated or more complex support organization than we had in the file. But for the example, so we have 4 different levels here, as you see. And then we have, you remember also that we were talking about maintenance capabilities, maintenance levels, like the I level, B level, O level, and so on. So here we call the levels, we name them from 1 to 3. So the first level is removing the engine from the helicopter. The second one is to remove the modules, like the sub-items, from the engine. The third one is to repair the actual engine or repair the modules of the engine. Okay, so that's 3 different levels. So meaning 3 different complexity levels of the tasks we need to perform. So typically maybe those are the easier one to perform, medium complex, and then the most complex tasks. So of course we can break it down and do it for each single task, for each single item, but then we have very many combinations to look at. But often this is, in reality you often look at complexity levels of the maintenance. Anyway, if we just limit all the combinations here a little bit, and we say that removing the engine from the helicopter is always performed at the base level. So we don't have to send, and this is quite common, I think, you are not transporting the entire helicopter back to some regional stations in order to remove parts from it. You can do that at the operational sites. And then you can send the engine backwards in the organization. But so for the sake of simplicity, in this case, we lock this level at the base, this kind of maintenance at the base level. But the other 2 ones, the level 2 and level 3, we're not sure where to perform them. We think that we can combine them as we want, the L2 and L3, at the 3 different levels. So that means that we get a set of alternatives. So for example, we can do, and maybe it's hard to read here, but I'll help you out. So either we can place the L2 level at the regional locations, and then we place the L3 at the central station. That's alternative 1. Alternative 2 is to keep the L2 at the regional and then move up the L3 to the central, to the OEM instead. Third alternative is move up L2 to the central level and do L3 at OEM. And last option is to do all 3 of them at the central station. So here are 4 alternatives that we think are sort of possible. And then we want to understand which of them is most cost effective in combination with the spare parts optimization and the resource allocation. We run this in OPUS 10. We get a standard cost effectiveness curve. It looks just as for any other OPUS 10 calculation. It's fast and so on, so it's sort of standard. We select a point here and so on. You get the cost and the effectiveness. But what's interesting here is that behind those points lies a lot of results. It always does. But when we run LoRa calculation, it also tells us which alternative for each of the points that is optimal. So in this case, we see that for the first section of this curve, it is the alternative 4 that is optimal, which means that we were performing all 3 types of maintenance at the central. And then, for the next part of the curve, we see that here's a section where it is optimal to perform the L2 maintenance, to move down the L2 maintenance to the regional level. And then, for the last part, we see that the most cost-effective alternative is then to move up the L3 to the OEM, but keeping the L2 at the regional. And this is the kind of answer you get. So, what's the best? Again, all 3 of them. What's the best location to perform the maintenance? How many spare parts at each location, and how many resources? So that's LoRa XT in OPUS 10. All right. Yeah, I think we sort of answered the question about maintenance optimization there, and I think the results were satisfactory, so we can move on. That was the last part from yesterday. I'll skip on here to continue talking about operational success and more about mission modeling, which is a little bit new area here. So the typical question then would be, can you, as our analysts here, analyst team, can you tell us the readiness for fulfilling a certain operational objective? Yeah, sure. And we can also tell you how our daily activities impact the readiness. So let's do simulation and study these questions. But before we do that, I'll show you some of the basic building blocks when we talk about mission modeling. And as you understand, there is something called missions in Simblocks as well. But if we just start by comparing availability and mission success. So we look at this truck here, and let's say that we have 10 of them in operation. Nice. And we know that the availability is 90%. It means that we have, on average, 9 of those. We have 9 of them available. There's always 1 in maintenance, okay? So 9 of them available, 1 in maintenance. And if the mission requirement is that we need 10 vehicles to even start a mission, we need 10 of them at the same time. What will be the probability of mission success? Well, it's 0%, because we never have 10 vehicles available. We only have 9. There's always 1 in maintenance. So this is just a maybe stupid example, but it's just to give you the understanding that availability is not the same thing as mission success, which also calls for the importance of doing analysis of mission capabilities as well, and not just staring blind at the availability number. Okay, so what are the building blocks in OPUS Suite? Well, of course, this is representing one mission. It has some length, what we call it duration. So it's the duration in hours of this mission. A mission can have a success point where we say that this mission is actually okay already. If it's 10 hours and after 8 hours, it's okay. We think that we completed the mission. So it's a successful mission if we do X out of Y hours. We can also define the number of nominal systems. That means how many systems are included when we start this mission. And if it's 4, might be. And then also we can give the minimum number of systems that we need to perform this mission, and it might not have to be 4. It might be okay that we continue to do it with 3 or 2, even 2 systems, and we still think that we can succeed with the mission. And another part of the building the missions is that there are different patterns of those missions. For example, we have first of maybe the most common type of pattern for the missions is what we call a fixed mission. That means that when a failure happens here, we stop the mission, of course, because the system needs maintenance, so the mission is stopped. But we will not continue the mission, even though it might be fixed. We still the mission is sort of over. We won't take it up or start it again. Then there is something called a continuous mission, which means that when that failure happens, we perform the maintenance, and as soon as we are ready with the maintenance, we start operating again with the system. So that's a continuous mission. And then we have what's called an extendable mission. Same thing as a continuous mission, but we won't stop. We say that this is 10 hours. There was a 2-hour maintenance stop here. It means that we will extend the length of the mission to perform those last 2 hours as well. So in this case, we were only operating for 8 hours, right? Because we were standing still for 2 hours. But with an extendable mission, we extend it in time, which means that we will operate for 10 hours, but there is a 2-hour interruption in the middle. Okay, there are also, a mission is the main building block, and with that you build an operational profile. And it works in a quite nice way, so that you typically start with defining your mission, and then you define it different levels of the usage of these missions. You build it up like a hierarchy. So, for example, we start with defining a week, which consists of 5 missions. Okay. And then we can define something like a month or a 3-week period, which consists of 3 weeks. So step by step, you build up the operational profile like that. So sort of iterative building blocks. And then you can also have different mission types, as I said, with all those patterns and so on. So that they can be different, and they can be different in length, and they can be combined. So we can combine different types of missions. Of course, for different type of systems, if we have multiple systems in our scenario or in our simulation, so we can combine them as we wish in time. So again, if you recall what I said a lot of times yesterday, it's recommended to start typically with a simple approach and build something simple, maybe like here. So just say that we have 200 hours per aircraft a year, split up in 10 missions. Something like that. Then you get a picture like this directly. So it's just a one-line input data. But then as you grow with your model and your experience and the information that you have, you might want to do really complex mission operational profiles. Like we were discussing with OPUS SUITE the other day. You have really high details if you're going on a deployment mission or something like that. So then you can build that as well. Okay, some short words around the results. So typically what we do is that we request submissions. That's the input of the model, right? So we say we want to operate like this with these systems and so on. And some of them will be fulfilled and some of them will not, okay? So, and this is, we saw this from the results from the simulation somewhat yesterday too. Green and red, good colors for showing good and bad, maybe. So anyway, these lost missions can also be, there are reasons for that. Why do we lose mission time? Well, maybe we don't have enough systems, or always it's that we do not have any systems that are operational ready. That's why we lose the mission time. So maybe the fleet size is not big enough, or there are other reasons that calls for the lost missions. And then they are represented as different states of the systems. So the system, if they cannot operate, there is a reason for it, and they can either be in maintenance, so we're actively working on the system in some way, or they can be waiting for resources. We're not working on the system because there is no personnel who can do it, or we can wait for spare parts. So we missed a spare part, so we're waiting for that. Okay. The operational profiles can be assigned just as we did for the system deployments yesterday at operational sites and units, and there are, of course, they need a deployment of the system, so there need to be systems defined at these sites in order to operate. And again, we can assign different operational profiles to all the different units and so on. Okay, so I'll move on to OPUS Suite. Okay, so now we are here again in OPUS Suite, and I'll open the file for the simulation here. And again, as I talked about yesterday, the suite is really integrated, so we can work with the same models in all of the tools. So before we looked at in the optimization, we were working with the OPI files, but we can use them both for the cost calculation that I did before, but also here for the simulation. So I have prepared a file here, and it's the same. It's a continuation of what we did yesterday. If you remember this helicopter variant that we were looking at. Okay, and we have, of course, the input tables, and here is a category called operations, where we have, yesterday we were looking at system deployments, which represents the number of systems at the different locations here. We also did, for the optimization, we just had the average utilization per year, but now we also start to build more complex operational profiles, starting from the missions. So here we have defined our mission here. We call it a mission daytime. We say that the nominal number of systems is 2. So we want to, when we take off for this mission, we leave with 2 helicopters, but we say that it's okay to continue as long as one of the helicopters are operational. So that's the nominal number of systems and the minimum number of systems. Right, and then we use the operational profile to build this up. And I'm going to show you a new a view that we haven't looked at so far. So far we've been looking at this, what we call the model view, which was the bottom up here, which is the model view. But here for the simulation, we also have something called a profile view. Because when we do the simulation, as we talked about yesterday, it's possible to vary a lot of parameters over time. And then we can use those profiles, we use the concept of profiles, to describe the time variations. So if we go here to the profile view, you see that we can select different stuff here. For example, operations, shifts, which means shift is something that is used to describe when the resources are available, for example. We can also do for transportations, we can say that during certain periods of the year, the transport is cut off. We cannot perform transportations every day, for example. And there are some other things that can vary over time as well. But now we look at the operation. And here you see our stations in the model. So we have the alpha station and the beta station where we have deployments. There are no deployments at the central. So here we can also drill down and see what those profiles look like. So we start with alpha base on the first level here, and as I said, it's built up iteratively. So we start with this profile, the OP for operational profile for alpha. Okay, and it's built up by the year alpha profile. So it's layer by layer we build up the profile. And the year starts at time 0, and we will do 5 of them because the total scenario length here is 5 years, just like we did with optimization yesterday. which is 43,800 hours. But so we do 5, see it says hours here. If I change that to years, it would be 5. But anyway, so we do 5 years on 5. Yeah, 143,800 hours. So, and then if we go down next level here, looking at how this year looks like. So next level down, so the year is built up by, first, there are 26 intense week missions or sub-profiles, and then we have call week sub-profile. So it's different. We have every second week it's a call week, and every second week it's an intense week. So we repeat them 26 times over the year. So that's how the year is built up. And then again, we go down one more level, looking at the intense week. So intense week, we do 28 missions within 168 hours. So 168 hours is 1 week, and we perform 28 missions. And each mission is 4 hours. And here we can also tell whether they start according to a schedule, or we can say that they are randomly or regenerative produced or started. So, but here they are scheduled. You see how they, in the profile view up here, you see graphically over the 168 hours how many systems that we have on mission. And if you remember, we had the number of system parameter that we gave for this mission was 2. So this is what we plan for. We plan for going out with 2 systems. Okay, and we can see things here like total system hours and so on. Oh, that's hard to read probably, but it says that in total we are planning to produce 224 hours with our system during this week. And then lastly, we have that call week as well, which is only 16 missions rather than if you remember, the 28 that we had for the intense week. We have 16 missions, but it's the same mission. So for 4 hours within that week. So that's how it's built up, and it sums up here. We can read the total system hours is 45,000 here for the alpha unit, and then same thing, of course, for the beta units, but there is only 9,000 hours. So we have fewer helicopters, and we do plan to fly less with them there as well. Okay, so that was the profile view and how we build operations. But I think the rest of the model is really the same. So this is actually the only addition we've done here to this more detailed description of the operations. But the rest of the model is the same that we were working on yesterday, with everything around the product breakdown and the reliability figures and so on. Okay, so that means that we are ready to run this simulation. Press the button up here. And again, you remember yesterday that we do a lot of replications. Each replication is a random draw, and then we produce the average value over all replications. Okay, so here we have again a lot of results. We started looking at it a little bit yesterday. But if we start looking at the mission time, we can accumulate, which means that we sum up over the entire period, the entire 5 years. So here we have the total value of. It seems that it's really small up here, but there are some hours that we actually don't manage to do, but it's not so many. Out of the 27,550 hours, we produce everything but 43.6. So that's kind of high mission success, right? Because this is the mission time that we are trying to achieve. But if you remember, we said that it was enough to produce to fly with one helicopter to say that the mission was successful. So if we instead look at what's called system time here, you see that it's higher. It's now over. I should do like this. You know what you can do here? You can lock the graph axis. So if I lock the y-axis, you see I get a red bar here. It's easier to, it's not changing the scale of it, so it's easier when I move here now. So you see, so system time is around 55,000 hours, but the mission time is only 27,000. And that's because we said that this is the actual tell how many systems that are operating simultaneously. So when we request for 2, which we do, it will be double amount of system time compared to mission time. So that's the difference between mission and system time. And so this is more of a measure of the operational availability. So how much can we operate with the systems? How many operational hours are we producing with the systems? And as you see, we lose more of that. We're not able to produce as much system times, but again, that's because we said it's enough to have just one system for the mission. Yeah, of course, we can also split this up and look at the different units. If I uncheck the box total units here, I see the difference between base alpha and base beta. And maybe as expected, we are losing more hours at the alpha base because we are trying to fly more there. Okay, so next type of result to look a little bit more at is the system. So this was centered around the missions, but if we move to the systems instead, and that's going to be really hard when we have locked the graph here to 70,000 because we don't have 70,000 systems, so it's really low here. So I'm going to unlock that y-axis and looking at the system results. And of course, we could have done float missions as well, but we can split this up over time. So here we see we have, in total, we have 9 systems. Yeah, exactly. We have 6 at the alpha base and 3 at the beta base. So that's 9. That was okay. All right. So we have 9 systems, and the different colors here represent the different system states. So the yellow is when we are on mission, and as you see, we have those weekly missions that we are trying to produce, and it's between 1 and 2. Here it seems as if we're never up to 2, but that's because we have pretty long, what's called result collection intervals, where so that's another thing that is aggregated in the results. If I change that, we can do that just to show you in the control table here, you see that here is something called the result collection interval. This means that the default value is 24 hours. So it means that we will, I mean, when you're about to present the result over time, you need to decide how wide each result box is. How do we split it up in bars for the different times? So to calculate the values. So you can set any value here if you want to aggregate per year, you can get that, or per month or per day, but I can also do it per single hour, like this. That means that the number of results is way higher because now I do 1 hour. That's also why the simulation will be much slower because I'm producing something like 57,000 results for each of the results. Something that you can notice here is that you might wonder why it pops up with I don't know if you can read this here. It says how many replication that is progressing in Simlogs. And this is a little bit interesting that my computer has 8 cores on the computer, which means that we can run 8 simulations in parallel. That's why we do 8 replications in parallel, so it jumps up with 8 every time. So there it goes. But I'll break the simulation here. We don't have to finish all 100 replications, but just wanted to show you how the result collection interval affects the results. Because now we will, for each hour, we will calculate an average value. And again, my computer is a little bit slow, but that was maybe a stupid idea to do this live, but This is the drawback when you come up with good ideas while demonstrating. You don't know how much time it will take. So, well, yeah, it was a bad idea. I realized that now. But anyway, I guess you realize that it's very, very many values that are processed here. So, come on. It was not the best case to show this. If you remember from yesterday, we were talking about, there it is, it took 50 seconds to save the results. You saw there was a green row there for a warning, and the different notices that you get here in the log window, they have different severity. So the gray ones are called notices, so they are not that much to think about. But then we have the green ones, which are warnings. They're probably good to read and try to understand why you get them, but you can still run the calculation. But however, the red ones are called errors, and they will stop the calculation. That means that there is something that the model doesn't understand, so we can't actually perform the calculation. So green ones are okay, but red ones will stop. And now I think I'm going to restart. Come on. And it's rather my computer that is a little bit tired today. Now, yeah. We'll start again.
Maybe we can run it over lunch and then we can show it.
Yeah, that's a good idea. We go back to where it was. Anyway, so you see that was the difference. Now when I use the 24-hour result collection interval, it goes much smoother. So, and then we have the results directly. So it was, as I said, not the best idea for a live demonstration. Sorry for that. Anyway, this was looking at the system results. You can do a lot of things here, but I think we showed that yesterday, but one important part is to look at why the systems are unavailable. So I select the system availability. I should select the system unavailability. And I get some different reasons, and you see that it varies over time because different things happen. We do have some spikes here, especially around here. That's kind of interesting. So I can zoom in the graph here a little bit. You see that here, it's in years, so it's kind of, we can do hours instead. So I can change the time unit to hours or days or whatever I want to have. But if it's hours, so after a little less than I have here, you see that we have a peak here in the unavailability. We have over 3 systems that are unavailable here for a while. And that's because what we can see, what's different here, is that we get this light blue bubble here at the bottom, which is that you get a PM. So many of the systems comes into PM at the same time. And what happens then is that, okay, so during this PM, we have this pink color, which says that it's an administrative delay. So there are delays in the administration of the maintenance for this PM. And that's something that you can add to the model. But in turn, we also have awaiting resources, which is the orange part. So, which is also pretty high. So we can see this, we get like we call it like a bump with high maintenance load. at this same point in time. That can be good to know because we might have to plan for that. And since it's a scheduled maintenance, maybe we can do this in a smarter way. We probably can spread it out. We don't have to do all the preventive maintenance at the same time because scheduled stuff can be, we can spread it out. And we can do that in different ways, of course. But one way is to, if you have a fleet of helicopters, after a while, the usage and the operational hours have spread out, so they don't start from zero and everyone has to go into maintenance at the same time, but it's more a stretched out procedure. So that means that they won't coincide like this, and that's something that can be taken into account because we can give something called age parameters on the systems and items. So you can specify where are we in the maintenance cycles in terms of preventive maintenance, of course. Random failures are independent of the state because of the Poisson process assumptions. But for scheduled maintenance, PM, you can define where in the cycle you are at the moment, which will give you a more precise answer when the maintenance will occur. So anyway, that what happens here. If I zoom out, you see that next peak load here is again, it's another light blue. But now, since as the systems or the fleet of systems are spreading out the usage, the PM will happen a little bit more differently. So it's more spread out. Some comes here and some here, and the tops are not as high anymore. So it was this first sort of top that was really high. Then it flattens out a little bit more. But we still see this effect from the PM that we have some peak loads on a regular basis here. Right. Let's move on. There are some other aspects of mission modeling as well. I take it quickly, but we can. So far, we've been sort of talking about straightforward missions, but there can be other things here as well that is interesting to know. That we can create dependencies. I'll talk more about it later. I can also create operational modes, which means that we can perform missions, but with different sort of readiness. So if for a helicopter, it might be that you have different equipment on the helicopter, and you have different type of missions. Sometimes you do surveillance, or you're doing search and rescue, or you're doing maybe warfare, or whatever it might be. So then you can have also different readiness for the different such capabilities to perform. And that can be described with operational modes. Formations is a way of saying that, okay, to do this, I need I need different types of systems at the same time. You can also have, for some missions, the reliability can change for different missions. So typically, if I'm doing some kind of engagement, the failure rates might be higher for the weapon systems or something like that. But if I do just reconnaissance, the reliability is lower. It's a more safe system, type of mission. And we can also model prioritizations of what type of missions are prioritized compared to other. But this is about dependencies. So for example, when we talk about helicopters, it might be that we can only do this mission while some radars are functioning so that we have communication with the ground. And if this radar function goes out of order here, it means that, okay, when I'm about to start this helicopter mission, it's not possible because there is no radar communication, so I can't do it. And if I have started a helicopter mission, I start to fly, and then all of a sudden the radar goes down, I also have to stop the helicopter mission. So these kind of dependencies between different system and different system missions and functionality can be modeled as well. Another example is pretty much as we had before. So anyway, here is something that is kind of interesting as well. If you want to go into details, I'll do it quickly just here. But talking about capability readiness. So a capability, again, it's what I mentioned before. So it's what I'm ready to perform. So can I do surveillance? Can I do engagement missions and so on? Here, I have 3 ones here: patrol, engage, and rescue. So those are operational modes in which I can operate with the helicopter. And then here's a concept that I haven't talked about yet, but it's something called functional block diagrams, or FBDs, which is the abbreviation that we use, and which is sort of commonly used as well, for reliability diagrams showing what type of subsystems that is needed in order to have a functional system. So, for example, here, to be able to do patrol, I need subsystem 1, 2, and 3. And I need all of them at the same time. To do the engage type of, to be in this operational mode called engage, I need 1 and 2, and then I need either 3, 4, or 5. So here, this is a typical parallel block, right? So it's a parallel structure. If you are used to reliability analysis, this is easy for you, you recognize it. But we typically talk about things that are in series. So here, all 3 have to work at the same time. That's a series redundancy or block diagram. Or it can be that it's a parallel one, like this. But so for the engage mode, we need 1 and 2, and either of 3, 4, or 5. And for the rescue, we need 1 and 4 and 5 in a series here. Okay, and then, for example, here, this subsystem 4, it can consist of a subset of items. So the subsystems are, this might be 3 different, that we have 3 different weapon systems, and to be able to engage, we need 1 of them in operation. Otherwise, we have to go back. And one such weapon system might also consist of a block diagram for its actual items in it. Okay, some other KPIs of performance is, for example, we can look at mission success rate. I showed this before. It's the number of missions that reach the success criteria. We can look at operational availabilities, which is the fulfilled system operational time, or the true or sort of availability of the fleet, which is more fleet readiness. So how many is ready for operation? That doesn't say how much we actually operate, but this is important. We compared this before, saying that this is the operational readiness, but this is more the system of fleet readiness. So, and that can be much higher, of course, but if you are not requesting any missions, maybe then we have more availability as well. And at the end, we have the reasons for unavailability that we've been looking at before as well. Okay, that was 1 hour of listening. I think it's time for a short break, 10 minutes maybe? 5 to 10 minutes. And we'll soon be back. Want to add something now, Jack? Or no, it's okay. Yeah, we'll take some break. We'll take a break. Thank you.
Just 5 minutes.
5 minutes is perfect.